Hi everyone, welcome to the 14.4 lesson on the chain rule. This is actually my favorite lesson in the class, mostly because it just makes really good logical sense. And if you're a math lover like me, things like this make things make sense and make them feel better because you can understand exactly why something is going on. All right, here we go. So you've learned a chain rule for functions of a single variable, and it had a definition behind it, very similar to the one we're going to refer back to in the last lesson. But let's read this theorem and then look at what's behind it. So we have two independent variables in a function. Okay, so we have the function w, which is a function of x and y. And it's differentiable if x is a function of t and y is a function of t are both differentiable. And we have our composite function is differentiable with this formula behind it. So we got to pick this apart because this is a lot of parentheses. So dw dt with respect to the change in time has two parts to it. Okay, we've got f sub x. Remember, this is a partial derivative, and then we've got x of t and y of t times x prime of t. So here's the chain rule going on inside here, and here's added to the derivative with respect to y of x of t, y of t times y prime of t. And so this is a nightmare, okay? All the parentheses are too much. So we're going to do this with differential notation. And so what I want you to notice some very specific things. This is the total differential, not in the x direction alone or the y direction alone because it has both components. But it is not a partial derivative because t is one single variable and it's the independent variable for both x and y. So this is not a partial derivative. Curly d, remember, is an indicator of a partial derivative. So the direct derivative of the function f in the x direction with the curly d's, and then the chain rule here, x prime of t turns into dx dt, but not a curly d. This is not a partial derivative because x is only a function of one independent variable. So it actually matters very much, by the way, whether you draw a curly d or a regular d. But in the end, it is the same idea. And notice how technically dx and dx would cancel if we were doing some algebra here. All right, same thing in the y direction. The partial derivative of f with respect to y times, for getting the chain rule, dy dt, not a partial derivative. All right, all of this is based on the this idea given in 14.3, the definition of differentiability. And this definition took place as these two functions, e sub 1, or these two values, e sub 1, or not e, but epsilon sub 1 and epsilon sub 2 were headed to 0. So these actually drop out. And you've got this idea of the derivative of the function in the x direction times the change in x, which is dx, right? And the derivative in the y direction only times the change in y, which is our dy. And all of this, notice there's no t here, but if we did dz dt, this delta turns into a d, right, in our differential notation, and the dt pops up here. So this is actually partial derivative of the function with respect to x times the straight up derivative of x with respect to t, and the same thing in the y direction. So we begin to understand this expression. But there's a diagram I want you to be able to draw to go with this to help you understand this. So here's what you understand in one variable chain rule applications. You have w, which is a function of one independent variable, x. So we start with a dependent variable on the top. The intermediate variable is x, and then the independent variable is t. So when we go from w to x, we do the derivative of w with respect to x, and then to go from x to t, the derivative of x with respect to t. We just multiply the derivatives as we go down, and here's the single variable derivative chain rule definition, okay, or formula. So here's what it looks like. It's called a branch diagram, by the way, for functions of two independent variables. So w is our dependent variable, and then along the middle, our independent variables, or excuse me, our intermediate variables are the independent variables of the first function, x and y, just like x was the independent variable of f up here, okay? So the first set of independent variables goes in the middle, the final independent variable, which everything is truly dependent on, is at the end. And then as we travel from one point to the next, we do a derivative. Well, see, since this point goes from a single point to 2 points, that's going to be a partial derivative when we choose whether we're moving with respect to x or with respect to y. Then, though, as we move back to t, that's not two independent variables, just one t is the independent variable here, so these are not partial derivatives. Just as we go from x to t, that's dx dt, not a curly d. And to take the derivative of all of w with respect to t, we're going to multiply everything along the lines. So we have these two derivatives multiplied here, these two derivatives multiplied here, and we take their sum to get the total derivative of w with respect to t. So this is a branch diagram. We're going to practice drawing those, okay? So we have our first attempt at using the chain rule here, a rather simple function, and so we're going to do this using our new method. There are other methods, and sometimes those other methods are easier, and sometimes they're not. So I'm going to show you both, okay? I want you to take note, we want to use the chain rule to find the derivative of the function w, which is x times y. With respect to t, so be careful and read the rest of the problem because there's no t in that. Along the path, x equals cosine t, y equals sine t. Okay, this along the path would be known to you if you had studied chapter 13 yet, but it's the same thing as just saying where x is cosine t and y is sine t, okay? What is the derivative's value at t equals pi over 2? Well, we'll answer that once we have the actual derivative function. So we're going to do a function w, and w depends on two variables. So we're going to do x on this side and y on this side. And both of those are functions of a single variable, so it'll come back together here at t. So to get dw dt, we have to first go partial because we have to choose whether we want to go x or y. So let me actually draw this nicely. Okay, so curly w, curly x. Either we're going to go that direction or we're going to go this direction, curly w, curly y. And then from x to t is a single variable function, so regular dx dt, or regular dy dt. And then we get down to our variable t. So we're going to multiply everything along the branches. Dw dt is partial derivative of w with respect to x, and dx dt on the left side of the diagram. And curly w, okay, curly d, dw dy times dy dt. I would like you to be able to draw both the diagram and write the chain rule for every one of these kind of questions. That's the skill you're going to be asked to do on the test. Not just find the derivative, but be able to explain this behind it, okay? So let's do that. So we're going to fill in these four expressions to get dw dt, and then we'll evaluate it at t is pi over 2, okay? So curly w, so the partial derivative of w with respect to x up here is y. And then we're going to do dx dt, well, here's x, dx dt would be the derivative of cosine t, which is negative sine t. We're going to have to come back and clean this up when we're done, but let's keep going. So partial derivative of w with respect to y is going to be up here, just x. And then the derivative of y with respect to t here is cosine of t. Okay, now we need to clean this up because we need our derivative in terms of t only. So y up here is sine t, so we really have sine t times negative sine t, which is negative sine squared t. And x is really cosine t, so we have cosine t times cosine t. So make sure that you're not leaving your answer with x's and y's in it, okay? Now, if you are picky and you feel like you need to put negative terms last, you can. I certainly would not require you to do this. And if you happen to notice that this is the cosine of 2t, that's fine too. I would take any of these three. In trig, sometimes some things aren't simpler. I would ask you to simplify The easier stuff, like if you have sine divided by cosine, I would expect to see tangent, that kind of thing. But I wouldn't necessarily require you to do these two. All right. There are some people that cannot abide a negative sign in front. It bothers me sometimes, but when stuff starts to get detailed and long, it doesn't bother me enough to do anything about it usually. But the last thing we have to do is to evaluate at pi over 2. So I'm going to go ahead and go with this one since that's easier. Cosine of 2 times pi over 2 is going to be the cosine of pi. And if you recall, pi over here is -1, 0. Cosine is the x-coordinate. And there you go. All right, example 1 is done. All right, so let's look if we have a function of 3 independent variables. So f of x, y, and z. It's much as you would expect. This is the step that's different. We have to include the sum of the partial derivative of w with respect to z times dz dt. And we expand our diagram to include a branch down the middle so that we have an intermediate node for all of our independent variables of the main function. So we still wind up with products, this branch times this branch here, this branch times this branch here, and this branch times this branch here. And once again, notice these are partial derivatives because w is a function of more than one variable, whereas x, y, and z are only functions of a single variable, so we don't do partials there. All right, and here we're not doing partials because we're including all of them together, and they are summed together to get the total derivative. All right, so let's try that. Oh, let me sneak back and tell you something I told you I was going to do. It is totally possible for you to do this. W is xy. Well, that means w is x, which is cosine t, times y, which is sine t. And then you could do dw dt without the need for multivariable calculus, as long as you're good at the product rule, which is what this amounts to in the end, because this is a simple product. But this will not get you full credit on a test. So if I say make certain to use the chain rule for functions of multiple variables, please do not do a substitution method. It will give you the same answer, but you won't get the same credit for it. And many of these are doable that way. And because these functions are uber simple, it actually is easier to do it with single variable calculus and substitution. But that's not the point here now, is it? Okay, so find dw dt if w is xy plus z, and x, y, and z are all functions of t, each and all differentiable functions of t. So in this example, the values of w of t are changing along the path of a helix. Do you recognize this set of equations as a parametric definition of a helix? Well, if we considered this x and y and we filled this into a sphere's equation now, okay, we could put the plus z squared equals r squared, but I just want you to focus on this part right now. If we did x squared plus y squared, that would be cosine squared plus sine squared. Now that would just be 1, wouldn't it? But the fact that z is increasing means that this is a spiral moving up off the xy plane, circling the z-axis on the at a constant radius all the way up. So you can learn to recognize these equations. They happen to give us the fact that it was a helix, but that's one that you might be able to reason your way through without having to be told. Okay, so what are in this example, the values of wt are changing along the path of a helix here as t changes. What is the derivative's value at t equals 0? So we'll evaluate this function when we're done. So dw dt, and again, multiple variables. We're going to do 3 pathways in this case, x, y, and z. And then each of those are just a function of t, so they're all going to come back down to one variable. That's t. So w's up here. This is beginning to look familiar. Now w is a function of 3 variables, so we have to do partials. And then regular derivatives here. So dx dt dy dt, dz dt. So please be able to draw this or to write it this way. W dz dt. Okay, so now we can fill it in. The partial of w with respect to x is going to be y, because x and z are constants with partials. Okay, dx dt over here, the derivative of x is cosine, or the derivative of cosine rather, is negative sine t. And dw dy is x times the derivative of y, which is going to be cosine t, looking a whole lot like the last problem. dw dz, if you look up here, this is a constant, so its derivative is 0. Derivative of z is 1. And that's times dz dt, which is just t, which is 1. So we have 1 times 1 here. Okay. So cleaning this up and substituting in x and y here to have our expression strictly in terms of t. Y is sine t, so we have negative sine squared t. X is cosine t times cosine t, so that's cosine squared t, plus 1. So here is our derivative function, dw dt. And when we evaluate it at t equals 0, we get negative sine squared of 0 plus cosine squared of 0, theta, 0, plus 1. So sine of 0 is 0 squared times a negative, negative 0. Cosine squared of 0 is 1, plus 1 is 2. And there we have our partial derivative evaluated at t equals 0. Okay, so this can go on for 3 variables like we showed, and this is expanding it even more. Okay, so not just for 2 independent variables, or excuse me, not just for 3 intermediate variables, but when the intermediate functions are functions of more than one variable themselves. Then notice every one of these little tiny derivative expressions are partial derivatives, because we now have x is a function g of r and s, y is a function h of r and s, and z is a function k of r and s. So it's all combinations of partial derivatives, and even this one's a partial derivative because we are taking it in the y direction only. Here we're taking it in the s direction only. So we're not taking any straight up derivatives of a single function or a single independent variable in this case. So notice the patterns here. We always do 1x1, 1y1, 1z1, and notice how these always match. Okay. Now, it doesn't make sense to cancel them because we need this definition as is, but if you're making sure you're drawing this right, please know the patterns in it. And then this one is always the one that we're taking the entire derivative in that direction. So these are all R for this one. Down here, they're all S. If you know the patterns, then you won't write out your chain rules wrong. All right. So we're going to first do dw dr. And we've been given functions of r and s for x, y, and z. So first thing we need to think of is the partial derivative of w with respect to r is going to be the partial derivative of w with respect to the first function x, and partial x with respect to r. That comes from here. And those are all curly d's. All right, partial w with respect to y, and dy dr, and then we do the z term, and dz dr. So that's going to be for r. Now this expression for s just puts an s there, and there, and there, and there. Okay, so now let's do the first one. The partial of w with respect to x up here. Well, these terms are constant in the x direction, and so the derivative of x is 1. The derivative of x with respect to r is going to be 1 over s, since s is a constant in that case. All right, make sure you know that's an s, not a 5. Here, partial with respect to y, well, this is going to be 0, and this is going to be 0. Derivative of 2y would be 2. And dy dr over here, with respect to r, would be 2r. The derivative of natural log of s with respect to y would be 0, so plus 0. And then here, the partial of w in the z direction, well, these are going to be, two terms are going to be 0 derivative, and then the derivative of z squared is 2z, and then dz dr. So over here, with respect to r, the derivative of z is 2. So cleaning it up, we get 1 over s plus, this is going to be 4r, this is going to be 4z, and then we can compare z is 2r, so let's go ahead and put that in. So cleaning it up, 1 over s is 4r plus 8r is 12r. That is the derivative with respect to r. So let's do the derivative over here with respect to s, just thinking about all of these as s here. So partial derivative of w with respect to s is going to be the partial with respect to x, which is 1, and then dx ds. Over here, I'm going to write x as r s to the negative 1. And if r is a constant, then that's part of the derivative. And then we have subtract 1 from this. And, oh, bring it down. Okay, so make it negative. So I just did the power rule on s to the negative 1 with a constant multiplier in front of it right here. Okay, dw dy is just 2. And dy ds over here with respect to s, this derivative is 0. This is going to be 1 over s. And then the partial with respect to z is 2z times the derivative of, partial derivative of z with respect to s. And over here, there are no s's in here, so that's 0. So our partial here is negative r over s squared. Please don't leave negative exponents in answers. Plus 2 over s. Okay, so could you do this more simply? Yes, you could substitute these values into the function and do it with no partial derivatives needed. We did review how to draw the branch diagram in a previous slide, so you might want to practice that, but it's done on a previous slide. And I want you to try example 4 on your own. So hit pause and go to page 825 and 6 and try example 4. It's just more of same, and I want you to see how that comes out for you. All right, moving on. I'm going to draw branch diagrams for a couple of different things. I want you to notice that we have f of x and y. Okay, and then we have x is a function of r and s, and y is a function of r and s. Now, what is that going to look like? Okay, I want to make sure that you're thinking about how this changes depending on what they give you. And there's a big old hint here. Okay, if I don't show you this part and ask you just to draw a branch diagram defining the function and asking for dw dr. I want you to be able to come up with the branch diagram and this on your own. But right now we've got this as a hint. We've got w up at the top. W is a function of x and y, so we would have 2 branches. And the variables go on the nodes. And then x is a function of r and s. Okay, well, we can't do 2 at the same time here necessarily, so here's what we're going to do. We're going to do 1 for r. And this is standard practice for them. They don't just keep branching out. And then we'll do 1 for s. Because you can't take the derivative of w with respect to r and s at the same time. You have to do them separately. We'll do separate diagrams. So since w is a function of more than one variable and g and h are functions of more than one variable, then everything will be a partial derivative here. And this going from x to r would be dx dr. And from y to r would be dy dr. And then over here, very similar. The top is the same, in fact. Partial derivatives all around. And then from x to s, we would have dx ds and dy ds. So be sure you can do this even if this is not given. Alrighty. I'm going to practice one more set over here. So if w is a function of x, a single variable, but x is a function of r and s, two variables, how does that change this? Well, we're still starting at w. I'm about to have a cat walk in front of my screen. There's Tigger. Everybody say hi to Tigger. Mwah. Go away, sweet kitty. She messes up my Wacom tablet when she walks on it. Okay, so w is just a function of one variable, so we're not going to have two branches. We're just going to have one, and it's going to take us down to x. But x is a function of two variables, so we need to branch out. So we're going to do r over here on that node and x over here on this node. And now we can draw the differential expressions. So we don't need partial derivative. Hi, Tigger. Might as well just let her walk. Go ahead. There you go. Keep going. Thank you, baby. See, that's what happens when cats jump into the game. Oh, it won't work on... Okay, we're just going to have the additional stuff from the cat. So now she's sitting here sweetly like she didn't do anything. All right, here we go. From w to x, we're going to have dw dx. See, and notice how that's the first thing here and here. I want you to be able to do this without these staring at you because that kind of gives it away. But if we want to go with respect to r, we have to do x is a function of two variables, so this is a partial variable, or derivative, excuse me. If we want it with respect to x, we're going to do curly dx, curly ds. And this covers both of these expressions. So you either go out this way, and that's one derivative, dw dr, and actually technically I should do that as partial because a later function is of multiple variables, so this can't be a straight up derivative. If you go down and over to the right, you end up with partial derivative of w in the s direction. All right, so be sure to be able to do those. Now, the last thing in this section is implicit differentiation, and we have a branch diagram to help us here. Let's look at our setup, okay? Here's all the if parts of a theorem, okay? So two variable chain rule in theorem 5 leads to this formula. Implicit differentiation is nobody's favorite in basic calculus, and this formula we're going to develop takes a lot of the algebra and number crunching out of implicit differentiation for functions of two variables. It could get very ugly, so we would like to have a little formula for this. So here we go. We've got w as a function of x and y, so we're going to put x and y here. And in this setup, look at this. The function f of xy is differentiable. Have to have that if we're going to do this at all. And when we have our function set equal to 0, that means y is defined implicitly, and specifically y is a function of x. Okay, so we have two things going on. We're going to have our function w equals f of xy, but also f of xy equals 0 because there is the equal 0 part is the part that implies that we need implicit differentiation, right? So we're going to follow this diagram. If we go from, well, y is a function of x, so we can do dy dx, which is, after all, what we want to find when we say take the derivative of y with respect to x in an implicitly defined function. But now that we've got a function of two variables, we need a little help here. Now, going from x to x, dx dx, well, that's just 1 because there's no change there. So this is how this is different from the other situations. So we're going to have the need to see my notes that my cat is sitting on. Come here, sweetheart. I know, you want to be in the show. Everybody wave bye to Tigger. That's her way of telling me it's time to go to bed. So we have this set up. You can't lay on my notebook. You're going to walk across the screen again? You can't sit there. Come on, baby. I always like a source of humor in the middle of a lecture. Where are you going to sit? You can't sit where you want to sit. Go. Sit there. Okay. All right, so maybe I'll edit some of that out and maybe I won't. Okay, so here's what we've got. W is a function of x and y, which is 0, and y is a function of x. Okay, so we can come up with our expression that we've used for dw. Okay, so if we do just in the x direction, dw dx, okay, if we take the derivative of this, well, the derivative of 0 is just going to be 0. I'm going to go ahead and put that out front. And then we need to take the derivative of this using the chain rule. So we will end up with dw dx in the x direction times dx dx. And that's this and this multiplied together, plus this and this multiplied together. dw dy, and see, this is an x because y is a function of x. Okay, the last one down here, dy dx, is the ultimate goal of this whole process, to implicitly take the derivative of y with respect to x. And this one is not a partial derivative, thank you, Tigger, because y is only a function of x and not of more than one variable. So this is a little confusing, more confusing than some of the other, but I think the diagram here helps me think it through very much better. Okay, so we really don't need this. We just need this expression because we're solving for the derivative of y with respect to x ultimately. All right, so we need to solve this equation. So ignoring all that, this expression equals 0, and we'll isolate dy dx. However, this is a lot of stuff, and I can clean this up a little bit because the partial of w with respect to x is, we're going to write f sub x. Okay, so there's our function named capital F. We're taking a derivative with respect to x. I love my sweet kitties, but they do get in the way. And dx dx is just 1, so we don't need that, times 1. Partial with respect to y, and then dy dx. That's the right-hand side. This is still just 0. Tigger is determined to sit on my Wacom tablet. Okay, so I will subtract f sub x. And then I will divide off fy. So we've got a formula, dy dx is going to be the opposite of f in the x direction divided by f in the y direction. So this is a formula that will save us much algebraic headache for implicit differentiation. So, by the way, there is extended to 3 variables. If you have x, y, and z, you do have this very, very similar derivation, so I won't make you walk through it. But we'll have sample problems for both of these, basically. So we want to remember them. So for example 6, we need to find dy dx for this function. So we earned it, so we're going to use it. Okay, so dy dx equals the opposite of the derivative, partial derivative of this expression with respect to x. So that's going to be 0 and negative 2x. And the derivative of negative sine xy with respect to x is going to be minus cosine of xy. And chain rule, we'll put the y out front here. Okay, so remember, sine of xy, taking the derivative just with respect to x makes y a constant, but we do have to apply the chain rule because we know y is a function of x. On the bottom, the derivative with respect to y. So derivative of y squared is 2y. Derivative of negative x squared is 0. And derivative of negative sine xy minus cosine xy. But this time, since x is the constant, it goes out front when we do the chain rule. Just make sure that agrees. Yep. So we have 2x plus y cosine of xy over 2y minus x cosine of xy. Now, that's just basically filling in a formula, which is kind of nice. All right, down here, oh, already did that. Dismiss, yay. Okay, derivative of z with respect to x and z with respect to y, and those were given too far. Down here, notice in our formulas, if you're trying to memorize these, well, y is on top, x is on bottom, and these are always flipped from that. In the direction of x is on the numerator, and in the direction of y is in the denominator, so it's flipped from the order here, and it's always opposite. Same is true down here with dz dx and dz dy. So that's how you can remember these. So for dz dx, I need the opposite of fx, fz over fz. Okay. So we'll evaluate this at 0, 0, 0 when we're done. And this is our last slide, by the way. So with respect to x here, we're going to have 3x squared, or the opposite of 3x squared. With respect to x makes that 0. Here we're going to have chain rule applies up here. X is our variable, so z is our multiplier. And there is no x in here, so that's all constant. In the bottom, fz, so 0, and 2z. Remember, my z's have bars on them. The derivative here is going to be y, and then the multiplier is x, e to the xz. And with respect to z here, it's just going to be cosine y. Okay, so I'm just going to take a shortcut. Distribute that minus sign this way. So there's our partial with respect to x. And then we evaluate it at 0, 0, 0. We get 0 minus 0. And then we get 0 plus cosine of 0. Cosine of 0 is 1. 0 over 1 is 0. And the partial of z with respect to y, it's going to be negative f sub y over s sub z. And we've already got that on the bottom here, so that's just a repeat. And it'll end up being the same down here. So when we get done, we'll have 1 on the bottom. F sub y, here we go. That's 0, that's 0. Here, we just have the constant multiplier e x z when we take the derivative with respect to y in the third term. And here we're going to end up with z as a constant. The derivative of cosine is sine, and we're going to change the sign to negative here. Derivative of cosine is negative sine. Okay, so when we substitute in 0, 0, 0, we get e to the 0, and we get minus 0. So we're going to have 1 over 1, which is 1. So that's the derivative in the partial derivative in the y direction for the function z. All right, that's everything. Thanks for listening.